Hello, ladies and gentlemen out there. I hope you're ready for more of our 2019 Euclid paper because we are looking now at question number 8. If you haven't given it a try, please consider doing so. As I said in our very first video, you can get a copy of this contest by clicking the link down in the description of the video. Okay, so feel free to pause it, try it out, but here we go. So there's two parts, A and B. A circle has center O and radius 1. Quadrilateral ABCD has all four sides tangent to the circle at points P, Q, R, S, and T as shown. I'm going to copy this picture because as soon as people start telling me things are tangent to a circle, there is one thing and one thing only that I like to do, and that is connect radii to the points of tangency. That doesn't have to be super accurate. I think theirs looked a little different than this, but whatever. Okay, so I think it was P here, Q, R, no, I thought there was a T. Oh, they skipped over R. Probably so that I could very nicely use that for the radius. I think I'm good, but that's okay. So P, Q, S, T. Okay. And so we connect up the radii, but when we do that, when you connect the radius of a circle up to the point where a line is tangent to the circle, you get right angles. You also get a bunch of other nice properties. So we've got these points out here, A, B, C, D. I think they went in that order. Okay. So there's another nice property. If I connect A up to O, for example, just to show you this property, I get two right angle triangles with the same hypotenuse and the same radius, so one of the legs is the same. So you can see AT and AP have to have the same value. And you do the same thing, PB and PQ and BQ, CS and CQ, and then SD and DT. These can all be shown to have the same value. This is just one of a number of circle geometry properties we can have. What else are we told? AOB is the same as BOC, is the same as COD. So all of these angles in here are the same. AO has length 3. Determine the length of DS. Okay, so DS is actually something I just highlighted. This is DS right here. So I know I've got 3 here. And we know, what was it? AOB. AOB. So this full angle here is the same as this full angle here. Oops, sorry. I'm going to have to color code these. Okay, so this angle is the same as this angle is the same as this angle is the same as this angle. So then they're all 90. Right? Unless I'm misreading this, they're all the same. COD, DOA. Yeah, they're all the same angle, and since they go fully around a circle, they must be 360. So, gotta actually write something out at least a little bit. So we'll say it's 90 degrees, since all four form a full circle. Okay, so I could actually now get rid of the green arcs and say, aha, we've got a 90 degree and a 90 degree and a 90 degree and a 90 degree. Okay, so what can we do from there? Are there... Yeah, it looks like we've got some similar triangles, actually. Notice that this point is inside this, that angle is inside this triangle, which is a right angle triangle, but it's also the same as for this triangle right here. So this angle and this angle are the same, and you can show this angle and this angle are the same, and these pink angles that I'm making new pink angles. Let's not be confusing. Let's give them their own color. Forest green, I guess, angles as well. Oops. There we go. So what can we say here? So notice that triangle ATO is similar to triangle AOD, just as an example. So we want to get down to SD. I want to get to SD. Oh, and this is also similar because with the orange dot up here, because the forest green dot there and the right angle here. So this is also similar to, we can even do it with this triangle here, which has the DS that I want. So maybe I didn't need to use these colors. So the orange dot is up at the O, so OSD. So that means that what? AO, which I know is 3, over OT, which I know is 1, is to AD over DO is to OD over, this is 3, this is 1, over SD, which is what we want. Okay, now. Wait, why did I say? Yeah, okay, yeah. AD and OD. Okay. So, what can we do here? So, OD is 3SD. And therefore, AD is 3OD, but we just said then that's 3 times 3SD, and which would make it 9SD. So AD is 9 times SD. I need to figure out what AD is, though. So if I get 3, 1, I'm going to get a 2 root 2 here because it's 8. So what do we have? AT. That's AO squared minus OT squared, square root of 8, 2 root 2. Okay. But then, using the same relationship, AT is to AO as AO is to AD. So this is 2 root 2 over 3. So AO is AO is 3. If we rearrange this, AO times 3 over 2 root 2 is AD. But AO is 3, so we get 9 over 2 root 2 is AD. And that's 9 times SD, so SD is 1 over 2 root 2. I'm sure there might have been a nicer... Oops. Oh, we're jumping around again. I'm sure there was a nicer way to show that, but I don't know, the thoughts escape me right now. There was probably a nicer, simpler triangle to work with. So I seem to recall when I did this question a while ago, it was a lot easier. I tried it when it first came out. The record is a long time ago, or a long time after, so that I forget what I did. But I seem to recall 8A being a lot easier than that. Oh well. Looks like it's just a bunch of similar triangles. Okay. B part. Suppose x so x is an acute angle. And we know cosine of 3 over 2 cos of a cos. And then is the same as sine of a sine. Ooh, this is interesting. Determine all possible values of sine 2x, expressing your answer in the... Oh, I don't like that pi squared there. A pi squared plus b pi plus c all over d, and these are integers. Okay, well, let's go to work on that. So what do we know? Cos 3 over 2 cos x is sine 3 over 2 sine x. So I'm tempted to make something equal to pi by 4, but I don't actually know that cos x and sine x are the same. Now I want sine 2x, don't I? We don't have any sort of... I know there are double angle formulas, but I've never heard of a 3/2 angle formula. Although I could use the half angle formula. On this expression. That might not be a bad idea. Is there anything else we might be tempted to do? My instincts are telling me maybe square both sides, but I don't see how that's going to help. I could maybe get... It could change this cos into a sine a little bit if I squared both sides. But I'm not seeing anything to go... where to go from there. I will try it. Do I want to get rid of the cos or the sine? I'm going to get rid of the... Well, we'll try the sine. Maybe we'll have to get rid of the cos for another reason. Okay, so I get a cos squared and then another cos squared is equal to 1. This is... No, this isn't particularly helpful. What do we want? We want sine 2x. And that's 2 sine x cos x. I'm most interested, why is there an a pi squared in this? This is an interesting question so far. Cosine of a cosine. Now the cos 2 times something formula is a cos squared minus a sine squared. But there are other ways to write that, of course. You could say 1 minus 2 sine squared, or cos squared plus 1. Now I do have an extra 1 lying around here. So if I add 1 to both sides, I'll get cos 3 cos x is 2 minus cos I don't like that it's cos x and sin. I wish there were a way to get rid of a cos x or a sin x and turn those around. Now I know x is acute, but I don't think that's really helpful at all. All I really did was make it cos of 3 cos 3 cos x, which can be expanded out into cos of cos x, but I don't see that going anywhere useful. Now, what if I wanted sine of 3 halves sine x plus 3 halves cos x? Maybe I need to start with a bigger expression. So this would be sine 3 halves sine x, cos 3 halves cos x, plus sine 3 halves cos x, cos 3 halves sine x. Now, if sine A is equal to cos B, then cos A and sine B are the same. If A and B are both in the first quadrant. Yeah. So that's true. So here's what I want to do. So x is in the first quadrant. So sine x and cos x are both between 0 and 1. And so 3 halves sine x, 3 halves cos x also are in the first quadrant. So when they told me cos 3 halves cos x is equal to sine 3 halves sine x, then I can swap the sine and the cos around. Okay, that's true. And then I don't think I want to use this one. Maybe I want to use sine minus. Yeah, I think that should do it. So sine A minus B is sine A cos B minus sine B cos A. So sine of 3 halves cos x, that doesn't really matter the order, sine 3 halves sine x should be sine 3/2 cos x, cos 3/2 sine x, minus cos 3/2 cos x, sine 3/2 sine x. And is this what I want? What I want is for things to sort of cancel each other out, and I don't think I'm going to get that. So instead, cosine. Let's try cosine. So if I do cos of a plus b, you get cos a, cos b minus sine a, or sine b, sine a, sine b. Right? So if we do cos of these two added together, then we'll have cos of the one minus sine of the other, but then this one is the same as this one, and this one is the same as this one, so this must be 0. Okay, so the cosine is 0. And that tells me 3/2 cos x plus 3/2 sine x, since, well, let's say since they are between 0 and 6/2, which is 3, which is less than pi, they must add up. The only value, the only angle in that range that makes cosine equal to 0 is pi/2. So that tells me multiply by 2, divide by 3, cos x plus sine x is pi/3. Okay, there we go. That's a nice observation, and we're starting to get rid of the. Well, you got rid of sort of the cos of the cos. Which is useful. So the sum of the sine and the cosine is pi/3. Does this doesn't ring a bell for me? Does this change any ideas or anything around? What do we need? We need sine 2x. So that's 2 sine x cos x, which I guess we can now say 2 sine x pi/3 minus sine x. So that's 2 pi/3 sine x minus 2 sine x, sine squared x. I don't see that going anywhere in particular. And there aren't really other formulations for sine 2x. Cos 2x, as I've already remarked, has a few of them. Although, now that I know that sine plus cos is pi/3, could we go back and use that? We can try it out. I got cos of 3/2 of cos x. I'm going to change that to cos 3/2 pi/3 minus sine x. And so that'll be cos pi/2 minus 3/2 sine x, which is, of course, equal to sine of 3 pi by sine x. That doesn't help. Do we have any other pieces of information? No, it's just the cos of the cos and the sine of the sine. That doesn't tell me anything new, and possibly is an observation I could have made another way. Okay, so cos and sine. Add to 3x. Now, what if I changed it to cos x? No, let's change it to, yeah, cos x is pi by 3 minus sine x. And then if I square both sides, this might be where I get my pi squared. So I'll get pi squared by 9 minus 2 pi by 3 sine. Ooh, I like that because we've got a 2 pi by 3 sine there. Plus a sine squared x. And that's equal to cos x, which is 1 minus sine squared x. Now, if I bring this sine over here and this over here and the 1 back over here, we should get 2 pi by 3 sine x minus 2 sine squared x on the left, and pi squared over 9 minus 1 on the right. But of course this, as I just remarked, is sine 2x. So the only value can be is pi squared over 9 minus 1, which they, I guess, want is pi squared minus 9 over 9. So A is 1, B is 0, C is minus 9, and D is 9. I don't think they actually asked us for those values. I think they just wanted this answer here. Okay, there we go. Yeah, so express my answer in the form. So determine all possible. We found the only possible. Okay. So we used sum of cosines, although as I found out later, I could have just used the fact that cos is sine of pi by 2 minus something. But yeah, I'd say it went well. Yeah, there we go. It had to be 0, and that gave us the inside had to be pi by 2, which then gave us this pi by 3 here. And that really sort of worked out. We just had to use it in 2 different ways. We rearrange it and square it, and then use it just straight from the definition. Okay. And that's it for 8. Both of them, both A and B, I feel like I could have done better or faster or slicker in a nicer way. But we got our answers either way. So there's question number 8, and we can move on to question number 9. If you haven't taken a look at that, I would encourage you to do so before joining me for that in the next video.